I'm Jim Lauria, Vice President of Sales and Marketing for Mazzei Injector Company. Waleed, thanks so much for allowing us the opportunity to present our technologies. So I started my career as a process engineer in the sugar industry. And one of the important lessons I learned early on was that in order to optimize, improve downstream processes, the way to do that was to optimize the upstream steps in the process to really improve that downstream process. And since filtration is an important process in almost all the water treatment systems that you would design, I'm going to talk about how optimizing these upstream processes can enhance and improve the economic benefits and the sustainability goals that a design might have. And so to meet these economic and sustainability goals, the first thing is energy conservation. Obviously, with what's going on with price of oil, natural gas, anything you can do to conserve energy is going to improve the bottom line. And also, you're going to reduce greenhouse gases. Another one is smaller footprint, not only in terms of real estate, but in terms of construction materials. So you're talking about steel and concrete, and obviously that's money. And also you're talking about to produce concrete, a lot of energy used, and you're talking about greenhouse gases. Decreased chemical usage, not only in terms of chemicals used in the process, but we've heard a number of times about using chemicals for cleaning membranes and other filtration media. Reduced maintenance, downtime. You're always going to be talking about if you're not having a piece of equipment working, that's going to mean that there's no water going forward, and that's time lost. Improve further downstream processes. And I'm going to offer a couple of case studies as we go through the presentation to talk more about that. Water savings, we talked about that. If you don't send water forward and you're wasting it, you're losing it, that's lost money. And then maybe most importantly at the end is employee and end user safety, important aspects. So the first case study I'm going to talk about is the city of San Angelo, Texas. And they were looking at surface water that they were starting to lose, and they needed to find another place to find their water supply. And they found groundwater, but the problem was that that groundwater was contaminated with radium, a radioactive material. So you can see those blue tanks in the back. Those are ion exchange resin beds, and that could remove the radium. But they also found that the problem was they had iron in the water, and they didn't want to use those resin beds to remove both the iron and the radium, short cycles, and really problematic. So they decided to use Mazzei injector, Venturi injectors to inject air to precipitate out the iron, and a secondary mixing device. You can see that on the right-hand side, a pipeline flash reactor that they could mount above. And that offered a couple of good benefits. So number one, they didn't have to break pressure coming from that groundwater source. And so they also got homogeneous mixing. And what that did was gave it a better particle size distribution to go to the media filters. So it offered longer filter runs, lower energy costs, and less backwash water, all improvements in energy. And they didn't have to build a basin where they'd have to break pressure. And also it reduced the amount of concrete and steel for this particular case study. Next case study was White Rock, British Columbia. And the advantage there was using Venturi injectors. They had to use ozone. They couldn't use air as an oxidant because they were trying to remove arsenic and manganese. And that was a good opportunity to use the Venturi injectors and then the secondary mixing device, a pipeline flash reactor again, so that they could improve the ozone mix and get a reduced amount of ozone, very high mass transfer rate for the optimized ozone contact time. And what that offered was they were able to get better mixing, lower amount of ozone, which meant that they could use less electricity on their ozone generator, less maintenance. And also another benefit was due to the increased mixing and reduced amount of ozone, they were able to reduce the potential of formation of bromate, which is a disinfection byproduct. And as same situation in the earlier case study, it reduced the footprint of the system, less steel and concrete, but also they had less real estate. And because they didn't have to put in these basins, they didn't have to expand the facility, which meant this location was in a forested area, so it reduced the number of trees that they had to remove on site. Next case study was the city of Wichita. This was an aquifer storage and recovery operation, and they were taking water from the local river. And because this was in an agricultural area, they were getting irrigation runoff with some herbicides, atrazine, and they needed to remove that atrazine before they put that into the aquifer storage and recovery system. So they were using an advanced oxidation system. And what that did was allow them to break up the herbicide and destroy it. But during the advanced oxidation process, they had some entrained gas, some gas bubbles. So they needed to remove those gas bubbles, and they put in these centrifugal degas separators to remove that so that they could improve the downstream process, the filtration process, and get more efficient filter operation. The next case study was Pure Water Monterey in California here. And in order to use and design the system most effectively for ozone treatment, which was at the start of the process, they used computational fluid dynamics. And this was important because the Pure Water Monterey process had to treat a wide range of different waters that they were using for the water reuse. Irrigation runoff, water coming from the municipal wastewater effluent, stormwater runoff. So they needed to be able to design this in such a way that would be effective to make sure it was prepared before the downstream filtration processes. So they had longer filtration life, improved microfiltration membrane performance, less cleaning of the membranes, obviously less chemical used, and improved downstream performance. And this is what the process train looked like. So the ozone was used both for disinfection to kill any pathogens, but also to help improve the filtration on that membrane filtration that was protecting the RO. So as I mentioned early on, to improve the upstream processes, if you start a process and it's inefficient, it's hard to recover from that inefficiency. So you really need to make sure those upstream processes are most efficient. And then there's one process that's gaining traction, ozone plus biologically active filtration, BAF. And basically it's ozone in front of some type of media filter. And that media filter can be sand, it can be anthracite, it can be activated carbon, and it has microbes on it that can digest organic contaminants. And what the ozone does is it breaks up those long chain organic molecules. So it makes those organic molecules bite-sized, if you will, pieces, so that the biologically active filtration of microbes on the substrate allow them to digest them. And this is important because now with this system, you're destroying rather than concentrating the contaminants. With RO, you're using the membranes to basically concentrate, and you've got to get rid of that concentrate, either in the ocean or in a deep well injection. And it also, the ozone plus BAF typically is a lower cost operation. And I just want to finish up with showing the different types of getting in these oxidants, and typically in the oxygen species, whether it's air, pure oxygen, or ozone. You can use fine bubble diffusers, but what we found is Mazzei Venturi injectors with either a basin nozzle manifold or a pipeline flash reactor offers a number of benefits. And I'd be happy to speak about those that anybody would like to talk about. Please connect with me on LinkedIn or with me on Mazzei at Lauria and Mazzei.net. and I'll be happy to talk more about it, or you can subscribe to my newsletter to Know Water is to Love Water, and I'll be happy to take any questions.
Thank you, Jim. Any specific question to Jim? I think Jochen had a question.
Yeah, hi, Jim. Thank you for your presentation. Very interesting.
Sure,
I may come back with some interesting project I have here in Switzerland where your injector may be interesting to replace some other injectors. But I have a question to the San Angelo. You mentioned that you produced narrow particle size distribution and that improved the media filtration performance for the iron removal. So what does it mean? It produced narrow particles.
So Jochen, basically it's putting in air, more homogeneous mixing. So we felt, based on some pilot testing, we saw that it was giving a narrow particle size distribution. And anytime you can have a narrow particle size distribution versus a wide distribution, it's typically better for that particular media filter. And so we had longer filter runs and less backwash water.
So that means you produced smaller particles, or what was the difference?
No, narrower. So within that range of particles, not necessarily smaller, just a narrow particle range that we could use going forward. So doing the pilot testing by putting in the right amount of air, that was the idea.
Okay.
Put in the right amount of air, get the right precipitation of the particles, and design the downstream media filters to meet those particles.
Okay. That means the main reason was to precipitate iron, correct?
That is correct. Before the resin beds,